Hi student, here I am discussing about optical activity and chirality. What is optical activity? Optical activity means a substance which can rotate the plane of plane polarized light either to left or to right. Such substances are known as optically active compound and this phenomenon is known as optical activity. So, what is the essential condition for a molecule to be optically active? A molecule possesses a chirality, then the molecule becomes optically active. So, what is chirality? Let's discuss chirality here. We know every physical object has a mirror image, but a chiral object has a mirror image that is different from the original object. Here, when we take the image of a left hand, it is look like the right hand. But we know when we place the left hand over right hand, it will not superimpose to each other. That means not match to each other. Such object and mirror images are known as chiral object. Chiral object. An object which cannot be superimposed on its mirror image is said to be chiral. In Greek, chir means handedness and the property of non-superimposability is called chirality. Thus our hands are chiral. Here the image of a conical flask is given. The flask and its image. When we place this object on this image, it will be superimposed to each other. It will exactly match to each other. So it can consider as a not chiral or ecchiral objects. If a object and mirror images are superimposable to each other, such object can be considered as a ecchiral object. Here also the image of the chair and the object are superimposable to each other. So chair is also is an example for a chiral object. And some chiral objects, example for some chiral objects are given. This is the screw and this is the mirror image. But here you can see that the screw is turned from left to right, but here it's turned from right to left. So these two are non-superimposable to each other. So these are example for chiral object. In the case of scissor also, these two object and mirror images are non-superimposable to each other. So this is also a chiral object. From some alphabet, some alphabet R, J, F and its mirror images of R and J and F are here. But this object, but in this case, these alphabets and its corresponding mirror images are non-superimposable to each other. So these alphabets are example for chiral alphabet, whereas A, M, O, these alphabets and corresponding mirror images are on this left side, but these are superimposable to each other. This alphabet can be considered as a chiral alphabets. So what about the molecule? Chirality in the molecule. Here an example is given CHClF Br. That means carbon is connected to 4 different atoms. This molecule image is this. Here you can see that this object and the mirror images are non-superimposable to each other. This molecule is an example for a chiral molecule. What about this? Here carbon is connected to 4 different atoms, but the 2 are same, 3 are same. This mirror image is this one, but these are not superimposable to each other. But when we rotate this image to 180 degree, we will get exactly same structure as the first one. These two are superimposable to each other. So this molecule can consider as a chiral compound. Next, cis 1,2-dichlorocyclopentane and trans 1,2-dichlorocyclopentane. In cis form, these two molecules are related as superimposable to each other. Okay, so this molecule is a chiral molecule, whereas in trans, you can see that these two are related as non-superimposable to each other. So this molecule trans form can be considered as a chiral molecule. So in this case of trans molecules, that means such a pair of molecules that are non-superimposable mirror images of each other are called enantiomers. So these two molecules are known as enantiomers or mirror image isomers. Their molecular formula is same, the structural formula is same, but only the difference is they show different property towards a plane polarized light. That means enantiomers have equivalent opposite rotation towards a plane polarized light. One enantiomers left the plane of plane polarized light towards the right, or one enantiomers turn the plane of plane polarized towards the left. Yes, one is dextrorotatory and other is levorotatory. All other physical properties of the enantiomers are same. So what makes a molecule chiral? If a carbon is bonded to 4 different groups, such carbons are known as asymmetric carbon atom or stereogenic carbon atom. Here you can see in this example, this carbon is connected to 4 different groups. One is methyl group, hydrogen, bromine and ethyl. When you take the mirror image of this molecule is non-superimposable to on its mirror image. So this can be considered as a chiral molecule. So this carbon is known as a chiral center. So if a molecule contains an asymmetric carbon atom, then that molecule should be chiral or optically active molecule. So if a carbon is connected to 4 different atoms, no matter how you twist and turn the model, they never look exactly the same. They are always different. So if a molecule possesses an asymmetric carbon, then that molecule becomes chiral in nature. So what makes a molecule a chiral? This example we already discussed this example. In this case, this molecule, the molecule carbon is connected with the four different groups, but among these 2 are same. The 3 are same. When we take the images of this molecule, this image is this one, but when we rotate this molecule to 180 degree, the image should be same as the first structure. So these 2 structure become not superimposable to each other. So this molecule can be considered as a chiral. There is the easiest way to understand the molecule is a chiral property by checking the plane of symmetry. Here you can see that if plane of symmetry is exists in this molecule, when we bisect the molecule through a plane, through the plane passing through the 1 and 2 atoms, then we will get exactly equal halves. So that means this molecule possesses a plane of symmetry. If a molecule possesses a plane of symmetry, such molecules are chiral in nature. That means if molecule is chiral if it has a internal mirror plane. Molecule is chiral if it has a internal mirror plane. So here this trans 1,2-dichlorocyclopentane, here no plane of symmetry. So you can say that this molecule is chiral in but it is not always true. That means if a molecule possesses not planar symmetry, it should be chiral, but it is not always true. We will discuss later. Molecule is chiral if it does not have a internal mirror plane. This is cis form of 1,2-dichlorocyclopentane. This molecule also possesses an internal mirror plane or a plane of symmetry. So this molecule is a chiral in nature. So what are the conditions for chirality? If a compound has no asymmetric carbon atom, it is usually a chiral. Second one, if a compound has just one asymmetric carbon atom, it must be chiral. If a compound has more than one asymmetric carbon, it may or may not be chiral. This point is very important. If a compound has more than one asymmetric carbon atom, it may or may not be chiral. So, identify the asymmetric carbon atom among the molecule. That means asymmetric carbon atom means if a carbon is connected with the 4 different atoms, then such carbons are known as asymmetric carbon atom. In this 4 carbons are there. Among this, only this carbon, the second carbon, is connected with the 4 different groups. So only this carbon is asymmetric carbon. The second example, 1, 2, 3, 4, 5, 6. Among the 6 carbon, only this carbon this is the symmetric carbon or a stereogenic carbon. Third one, 1, 2, 3, 4, 5, 6. Among the 6 carbon, only this carbon is connected to 4 different atoms. One is hydrogen, one is COH, one is CH3, one is propyl group. So this is the stereogenic center in this molecule. So this is a large molecule. In this one, this carbon is stereogenic because this carbon connected to 4 different atoms. One is hydrogen, one is methyl, one is OH, and one is this part. And this carbon also connected to 4 different group 1, 2, 3, 4. Next one, this carbon also possesses symmetric carbon. So here 3 asymmetric carbon or stereogenic carbons are there. In a molecule, if a molecule possesses n number of chiral carbon or asymmetric carbon, then that molecule shows 2 raised to n stereoisomers. 2 raised to n stereoisomer. If n is equal to 1, 2 raised to 1 is equal to 2 stereoisomers are there. N is equal to 2 raised to 2 is equal to 4 stereoisomers are there. So, the example, first one is lactic acid. Then this is a structural formula of lactic acid. Lactic acid COH, CHOH, CH3. In lactic acid, this carbon only connected to 4 different atoms. So, only one stereogenic carbon is there, whereas one asymmetric carbon is here. So, this molecule shows 2 raised to 1 stereoisomer, that is equal to 2 stereoisomer. Okay. In the lactic acid, mirror image is given in this left side. So, this one is the mirror images of the lactic acid. You can see that this is not superimposable to each other. So, this is a chiral. These are known as enantiomers. That means both the enantiomers show a specific rotation magnitude of 3.82 degree at 298 Kelvin. That is D lactic acid. D means which rotate the plane of plane polarized light towards the right, shows plus 3.82 degree, and L lactic acid means or minus lactic acid, that means which rotate the plane of plane polarized light towards the left, show minus 3.82 degree specific rotation. Specific rotation of an enantiomers are equal and but opposite in rotation. So cancel each other. So cancel each other here. This is the plus lactic acid. Plus lactic acid means which rotate the plane of plane polarized light towards the right. This is the minus lactic acid which rotate the plane of plane polarized towards the left. So left component and right component are cancel each other. So they are and they show optical inactivity. Such optical inactivity is known as optical inactivity due to the external compensation. That means the plus form of the one molecule is cancelled by the plus minus form of the other molecule. So such optical inactivity is known as the optical inactivity due to the external compensation. In other words, the equimolar mixture enantiomers is optically inactive due to external compensation. Such an enantiomer, that means equimolar mixture of an enantiomers of a substance is called racemic mixture. Equimolar mixture of an enantiomer is known as a racemic mixture. Racemic mixture. Racemic mixture is optically inactive due to external compensation. Next example is tartaric acid. The formula of tartaric acid is COOH, CHOH, CHOH, COOH. Okay. How many stereogenic carbon or asymmetric carbon is present in tartaric acid? Only 2 stereogenic carbon. One is this one. Here, carbon is connected to the hydroxyl group, this group, and this side, and here only hydrogen is present. And other stereogenic carbon is this one. So 2 stereogenic carbon is present in tartaric acid. So tartaric acid show 2 raised to, in the case of tartaric acid, 2 raised to 2 stereoisomer is equal to 4 stereoisomer. Okay, these are the possible 4 stereoisomer. This is the first structure, COH, OHH, HOH, COH. Okay, OH and OH groups are alternately arranged. The second structure is exactly equivalent to the mirror images of the first structure. So structure 1 and 2 can be named as enantiomers. But the structure 3, both the hydroxyl group are on the same side. And structure 4 is the mirror images of the structure 3. But when you looking at the structure 4, if you rotate the structure 4 to 180 degree, the structure will be exactly equivalent to structure 3. That means if you rotate the structure 4 to 180 degree, then the structure will be exactly equivalent to structure 3. So structure 2 is equal to structure 3. So we can consider these two structures as one. Both are same. So instead of 4 stereoisomer, tartaric acid shown only 3 stereoisomers. Okay, these two are same. Next, let's discuss the optical activity of these isomers. First one is first and two structure. This is the first structure and this is the second structure. These two structures are related as a object and mirror image, but they are not superimposable to each other. So these two isomers can be, stereoisomer can be named as enantiomers. Enantiomers of tartaric acid. This is the third structure of tartaric acid. Here you can see a plane of symmetry exists in this molecule. That means when we bisect the molecule through this plane, we will get two equal halves. So this and this structure, this will be optically inactive. So this stereoisomer of tartaric acid is known as mesotartaric acid. Mesotartaric acid. So and then this is the first structure of tartaric acid. In the first structure, that it means this structure, optical activity studies shows that this is two stereogenic carbon atom. The tartaric acid rotate the plane of plane polarized light towards the right. That means the first structure rotate the plane of plane polarized light towards the right. the molecule has no plane of symmetry. The optical rotation due to the lower half of the molecule is strengthened by that due to the upper half. That means this is a one stereogenic carbon. If this part rotate the plane of plane polarized light towards the right, the upper part also rotate the plane of plane polarized light towards the right. That means then if this rotate the plane of plane polarized to 6 degree, the upper part also rotate the plane of plane polarized light towards 60 degree. So 6 degree plus 6 degree, the net result is the total, it shows plus 12 degree rotation. 12 degree rotation of plane polarized light. Whereas this is the second structure. Second structure, optical activity studies shows that this structure shows negative rotation. That means which rotate the plane of plane polarized light towards the left. This molecule also possesses no plane of symmetry. Optical rotation due to the lower half of the molecule is strengthened by the upper half. That means this part, if the rotate plane of plane polarized towards the left, the upper part also which rotate the plane of plane polarized towards the left. As a result, which shows a minus 12 degree rotation towards the left, minus 12 degree rotation. Okay. Whereas mesotartaric acid is optically inactive. It is optically inactive due to internal compensation. That means if the lower part rotate the plane of plane polarized light towards the right, then the upper part will rotate the plane of plane polarized towards the left. Okay, if the one part rotate towards the right and the other part rotate towards the left, as a result, two effects will cancel to each other, hence which shows optical inactivity. Such optical inactivity is known as optical inactivity due to the internal compensation. That means optical inactivities occur due to the internal rotation among this molecule. Internal rotation, one part rotate the plane of plane polarized light towards the right and the upper part rotate the plane of plane polarized light towards the left. So cancel each other. So optical inactivity here is due to the internal compensation. So then the new term diastereoisomers. Here the three structure of tartaric acid is given. Structure 3, 1, 2. We already discussed about the structure 1 and 2 are related as object and mirror images. So they are known as enantiomers. But here these are the three stereoisomers of tartaric acid. But the specialty is that the three structure and one structure is related as they are not mirror images. Similarly, the 3 and 2 structure are related as they are not mirror images. They are stereoisomers of tartaric acid, but they are not related as mirror images of to each other. So such stereoisomers are known as diastereoisomers. That means diastereoisomers are stereoisomers which are not mirror images of each other are called diastereoisomer or diastereomers. So this term we already discussed, racemic mixture. That is racemic mixture means an equimolar or 50-50 ratio of mixture of two enantiomer is called a racemic mixture or racemate. Enantiomers have identical chemical and physical property except their effect on plane polarized light. They rotate the plane polarized light equal and opposite direction. So their